Let me welcome you to this lecture. We will now discuss the chemistry of main group organometallic compounds. And during our discussion on main group organometallic compounds, we will primarily focus on the bonding properties of these compounds as well as the reactivity of these compounds, and we will refrain from discussing the preparation of these compounds because preparation of all these main group organometallic compounds essentially follows similar routes, and you are advised to consult the book in order to learn about the preparation of these compounds. So we will discuss mainly the bonding properties of main group compounds as well as the reactivity of these main group compounds. Now the reactivity of the main group compounds are important for us because many of these main group organometallic compounds, like say for example the Grignard reagent or organolithium compounds, they are important reagents in organometallic as well as in organic chemistry, and that is why we will primarily focus on the reactivity of these main group organometallic compounds. So let us begin our discussion on main group organometallic compounds by starting with this organolithium compounds. So these organolithium compounds are very important reagents in organometallic chemistry. Let's say for example organolithium compounds like butyl lithium, N-butyl lithium or butyl lithium, they are very important reagents. Now these compounds are highly pyrophoric in nature because they react with both moisture and oxygen. So whenever you have a reagent of this organometallic lithium reagent you wish to use, one needs to find out the exact concentration of the compound in solution before using the reaction, using these reagents in reactions in stoichiometric quantities. So one needs to have an assay, or one needs to have a way to find out the concentration of these organolithium compounds. So one of the ways to do volumetric titration with water. So if we do volumetric titration with water, there is a problem. That is, if one reacts organolithium compound, if one titrates organolithium compound with water, what one gets is RH plus LiOH. This LiOH, lithium hydroxide, can now be titrated with acid to give us during this titration one usually gets an excess of RLI concentration is found than what is actually present, because along with RLI what we will have in the solution is also ROLI, because this can form from RLI itself, from lithium organic RLI, by reaction of this RLI with dioxygen essentially gives us this. So the compound or the solution containing RLI is contaminated with ROLI. Now this ROLI can also react with water to give us ROH plus lithium hydroxide, which again will react with the acid that we are going to titrate with, and that is why in this titration one usually ends up with higher amount of RLI the titration gives us than what is actually present. So this titration is slightly modified, or a double titration method has been developed for this purpose, for estimating the concentration of RLI. That is, this method is by Gilman and it was developed in 1964. So what one does is So if one starts with M equivalent of RLi plus N equivalent of ROLi is present, then it will react with M plus N equivalent of water to give us M plus M equivalent of RH, N equivalent of ROH, and M plus N equivalent of LiOH. So this M plus N equivalent of LiOH will now react with M plus N equivalent of HX and acid to give us now. Apart from this titration, what is also done is another titration is carried out. This is the first titration where the mixture is essentially allowed to undergo hydrolysis, and then the resulting lithium hydroxide is titrated with an acid to get to find out the amount of both total RLi and ROLi that is present in the mixture. Then what is done? The mixture is in the second titration. The mixture is treated with first with this dibromoethane, which will react with RLi, not with ROLi, and that is why what is going to form is RBr is going to form. That is M equivalent of RBr is going to form, and M equivalent of C2 that is this ROLi will not react with this dibromoethane and it will be left intact in this reaction, and that is why LiBr, that is N equivalent, and plus M equivalent of C2 A6 is also going to be formed. So now this ROLi that is left after this reaction is essentially now hydrolyzed to give us so this N equivalent of LiOH is now titrated with acid to give us so we can find out during these both of these two titrations. In titration 1 we use M plus N equivalent of acid, and in the second titration we use M equivalent of acid. So the difference of the equivalent of acid, that is M plus N minus N equivalent of acid, will essentially give us the exact amount of or exact concentration of RNI in the solution. So this is the double titration method that was developed by Gilman in 1964 for estimation or finding out the concentration of organolithium reagents RLi in a given solution. Then more recently, direct methods for estimation of organolithium reagents are developed. So in this case, one uses a reagent that is 4-hydroxymethyl biphenyl, this which will react with RLI to give us, when it reacts with one equivalent of RLI, it produces the lithium salt. So the hydrogen atom on the hydroxyl group gets deprotonated here, and what we will have is this salt is formed, and this salt is colorless in nature. Now once you add excess of RLI, once you add one drop of RLI in excess, this will react with this salt then, and next it is going to abstract one of these benzylic protons over here. So what we will have is this sort of compound is formed over here, and this compound is in orange red color. So the moment you add an excess amount of RLI, you see that an orange red color is developed in the digestion media, and from here one can find out the exact amount of RLI present in a given solution, because during this titration we can find out the amount of RLI in the solution. So these are the methods to find out the concentration of RLI, because one needs to use the organolithium reagents in stoichiometric quantities, different reactions, and that is why knowing the exact concentration of the reagent is important, because these reagents tend to undergo decomposition in presence of air or moisture. One needs to find out the concentration just before performing the specific reactions. So then let us go and discuss about the bonding in these organolithium compounds. Now one of the most important feature of these organolithium compounds is that they tend to form oligomers in solution as well as in solid state. Say for example, methylithium exists as a it exists as a body-centered cubic tetramer, that is, it exists, the methylithium exists as a tetramer in solid state as well as in different solutions like THF or ether. It exists as a tetramer. So let us draw the structure of this tetramer. It has a cube-like structure where the lithium atoms occupy alternate corners of the cube, and the methyl groups are actually occupying the remaining alternate corners of the cube. So let's draw the structure of these. So this is how it is. The structure of methyl lithium, we see that it is cubic in nature. It has cubic tetrameric units are present in the solid state structure. And also one more particular point that we should note here is that these methyl groups of one of these tetrameric unit also interact with lithium atom from a nearby tetramer. So there is also interaction with lithium atom of a nearby tetramer, and these sort of intermolecular interactions are responsible for low volatility of these organolithium compounds, because they are of low molecular weight, we see, but still they are less volatile because of such strong intermolecular interactions are present. And also this accounts for the the insolubility of these compounds in non-solventing solvents. Say, for example, methylation is insoluble in hydrocarbons because of these strong intermolecular interactions. So we needs solvating solvents. Only then these are going to be soluble in those solvents. Now, tertiary butyl lithium also has similar tetrameric structure in, say for example, hydrocarbon solvents. Now, these tertiary lithiums are much more volatile as compared to methyl lithiums. Here, as we can see that the distance, because of the steric bulk of these tetrameric units, the interaction of the butyl groups or methyl groups on these butyl substituents with the nearby lithium group atoms of the nearby tetramer are weak as compared to what we see in case of methyl lithium, and that is why tertiary lithium is much more volatile than methyl lithium, and also this tertiary lithium is soluble in hydrocarbons like hexane. So that is that we see that from the because of intermolecular interaction plays a role in determining the solubility as well as the volatility of these organolithium compounds. Also, the nature of solvents determine the nature of aggregation or oligomerization that happens in these organolithium compounds. So for example, in different solvents, the aggregation pattern of organolithium compounds are different. So methyl lithium, if we take methyl lithium, so in THF or in ether, it exists as a tetramer. But if we take is donor solvent, that is TMEDA, tetramethyl ethylene diamine. This is tetramethyl ethylene diamine. It is a donor solvent because the nitrogen atoms can go and coordinate to the lithium center over here, and that is why in this solvent we see that the methyl lithium does not exist as a tetramer, but it exists only as a monomer. Then we see that in the N-butyl lithium, which is again a very widely used organolithium reagent, in cyclohexane solvent, it exists as a hexamer, but if you use THF or ether, it exists as a tetramer. Then if you take butyl lithium instead of N-butyl lithium, so then in hydrocarbon or in hexane, it exists as tetramer, but in THF or ether, it exists as a monomer. So this also tells us about the difference in intermolecular forces in these compounds, different organolithium compounds. What we see is that methyl lithium, where the intermolecular interaction is quite strong, can exist as a tetramer even in donor solvents like THF or ether, while we need strongly sigma donor solvents like TMEDA to have a monomeric methyl lithium compound. But the tertiary lithium, where the intermolecular forces of interactions are quite weak as compared to what we have in case of methyl lithium, it exists as a tetramer in hydrocarbon, but the moment we use weakly donor solvents like THF or ether, we get it in monomeric form. So the nature of aggregation, we can play with the nature of aggregation by changing the type of or the nature of the solvent that we use in case of these organolithium compounds. Now, one question that we should ask at this moment is why such aggregation patterns or why such organolithium compounds undergo such aggregation. So, if we look at the orbitals on lithium, we will be able to answer this question. So, it is 2s, and what we have valence orbitals on lithium, that is 2p. So there is one electron in the 2s orbital of lithium, and it uses this electron to form a covalent bond, or we say form a bond which is largely covalent in with alkyl group or sp3 hybridized carbon atom in of this alkyl group. But now it cannot achieve the octet structure by forming this kind of bonds, because these orbitals, valence orbitals, will remain empty in such a bonding pattern. And in order to use these valence orbitals, actually, they undergo aggregation, and this essentially leads to formation of multi-centered bonds that we have seen in case of electron deficient elements like boron. So that is what happens when these alkyl lithium or organolithium compounds undergo aggregation. They form multi-centered bonding. We'll see how they form the multi-centered bonding. So to understand this process of formation of multi-centered bonding, let us take methylithium as the example, which exists as a tetramer in the solid state. So methylithium, if we take, there is a Li4 tetrahedron we see, and this tetrahedron, let us take the Li4 skeleton, and in this skeleton, all the lithium atoms, they are sp3 hybridized, and if we look at the skeleton in this way, so we are looking at the tetrahedron from the top. So there is this middle lithium atom is there, and all of these lithium atoms are sp3 hybridized. So now, if we use if we look at the this skeleton, we will see that there are two different types of sp3 hybridized orbitals in this. In all of these lithium atoms, one of the sp3 hybridized orbital points along the C3 axis of symmetry that passes through the respective lithium atoms. So, for example, for this lithium atom, one of the sp3 hybridized lobe will be pointing upwards towards, perpendicular to the plane of this board, which is through which this C3 axis of symmetry essentially passes through. Now, the other three, this particular sp3 hybridized orbital, we will call it the axial sp3 hybrid orbital. So we have one such axial sp3 hybridized orbital, and apart from that, we also have three more sp3 hybridized orbital, which we call the tangential sp3 hybridized orbital, as they are pointed towards the normal of this triangular face over here. So there are three tangential sp3 hybridized orbitals. So now these tangential sp3 hybridized orbitals on the lithium atoms essentially are involved in forming multi-center bond within a tetrameric unit. So how it happens that, so let's take tangential sp3 hybridized orbital on each of the three lithium atom on one triangular face of this Li4 tetrahedral skeleton. So we can have these orbitals can now form molecular orbitals, or we should rather call them as metal group orbitals, which are going to bind with the orbital from the sp3 hybridized orbital from the CH3 fragment in methyl lithium. So we can have three different combinations of these sp3 hybridized orbital. In one of the combinations, all of the sp3 hybridized groups are in the same phase. In the another one, we have one node where, so we can have one node over here, and this particular orbital can be in phase with either with this sp3 hybridized globe or this particular sp3 hybridized globe. So we rather not draw this particular lobe, and we know that in this case we have one node, and then we have a system where there are two nodes are present. So we can have this particular combination as well. So we have three combination of these sp3 hybridized orbital of the lithium atoms, and these essentially form the metal group orbitals. Now the CH3 ligand, CH3 group or the sp3 hybridized orbital of the CH3 ligand, CH3 group can now come and bind with these metal group orbital of the right symmetry. So what we have is here C H H. So it can now interact with the metal group orbital of the right symmetry. The sp3 hybridized lobe of the CH2 group can now interact, and this way a four-centered two-electron bond is essentially formed. We can also draw the molecular orbital diagram here. So this is the energy scale. The orbital of carbon, which contain CH3, which contain sp3 hybridized orbital of CH3, which contain one electron here. Then we have the metal group orbital. This is three metal group orbitals of this Li4 skeleton over here, and one of the metal group orbital that is of the right symmetry will interact with this sp3 hybridized orbital of the CH3 fragment, and this is how the molecular orbital diagram will look like. So these two, the other two MgO metal group orbital will remain as non-bonding molecular orbital, and this essentially all of these three together contain one electron. So that will essentially leave us with two electrons in the bonding molecular orbital here, and then from here what we see is that this essentially forms this four-centered two-electron lithium carbon, as well as this also brings in lithium interaction. So this molecular orbital picture not only gives us this lithium carbon interaction in this methyl lithium, but also it also gives us the lithium interaction, which gives this all of these three lithium groups together because of this four-centered three electron bonding. So now the total four CH3 fragments are there, and each of these lithium atoms, which contain one electron now, can form four such four-centered two-electron multi-centered bondings with these CH3 groups, and that essentially forms this tetrameric structure in methyl lithium. Also, this essentially leaves the axial sp3 hybridized orbital of um, this Li4 skeleton over here. This remains unoccupied during this 4 center 3 electron uh, bonding with the CH3 groups within this tetrameric unit. So this particular axial sp3 hybridized orbital of the Li4 fragment or skeleton is essentially used for interaction of this lithium atom within a tetrameric unit to interact with CH3 groups of a neighboring tetrameric unit. So this this sp3 hybridized orbital or the axial sp3 hybridized orbital can be now used for interaction with intermolecular interaction, or also this can be used for interaction with sigma donor ligands or sigma donor solvents like TMADA, which can essentially which can come and which can donate electrons to this sp3 hybridized orbital or empty sp3 hybridized orbital of uh, the the Li4 skeleton. So we have now understood the reason for this aggregation pattern in organolithium compounds, and at the same time we have understood the reason why for these intermolecular interactions, or the reason why donor solvents can uh, break down these aggregations in organolithium compounds. So let us now discuss about the reactivity of organolithium compounds, and one reaction that we should begin with about the reactivity of organolithium compound is the methylation reaction, because organolithium reagents are essentially used for methylation with different substrates, and then we can proceed further, or we can do other reactions on these the products that we obtain after the methylation reaction. So the we can do methylation reaction. First reaction is the methylation reaction with another hydrocarbon. So RLI can react with another hydrocarbon over here to give us R-Li plus RH. So metal is essentially exchanged. This reaction will proceed, or this equilibrium is essentially favored towards the right direction only when RH or the CH acidity R-H is higher than RH. So the CH acidity of this hydrocarbon must be higher than the CH acidity of the hydrocarbon that is going to form during this reaction, and only then the reaction is essentially, or the equilibrium is essentially favored towards the right direction and the reaction proceeds. So now if we take example of two CH acids, and if we look at the pKa of these acids, so pKa, so this is around 37 pKa, and if we take and butane, that is around 44. So what we see is that benzene is a better CH acid as compared to and butane over here. So if we go by this logic that the stronger CH acid will react with to form the weaker CH acid over here, so then this reaction should be possible. that is, let's take cyclohexane as a solvent. So, but this reaction is extraordinarily slow, and this reaction does not proceed actually uh, as we expected from this. That if we have a the stronger or better CH acid will essentially more acidic CH acidic compounds will react with RLI to give us a less acidic CH acidic compound over here. And this reaction, though it is supposed to uh, proceed towards the right direction based upon that particular logic, but the rate of this reaction is extraordinarily slow. And only when you use TMADA along with uh, you add TMADA to this reaction, a mixture denominator reaction proceeds. And the reason is because TMADA can because this N-butyl lithium exists as a hexamer in cyclohexane, and that is why uh, it does not react with the substrate. And also TMADA does one more thing, that is so it exists as a hexamer in cyclohexane, this is 6H12. So if we add TMADA is going to go and coordinate with the lithium. Also, apart from breaking down the hexamer into monomeric form now, the reagent is now in monomeric form, it also changes the polarity of these lithium carbon bonds. So and so that the butyl group, N-butyl group is now more carbon ionic, and that is why its reactivity has increased much more as compared to what you had in case of this hexamer. And now it can react with benzene to give us the product in this way. So the reaction proceeds only when TMADA is used as a co-reagent, or otherwise the reaction does not proceed, or the methylation reaction does not proceed for completion. So the other type of reaction, important reaction of these these organolithium reagents is that deprotonation of phosphonium ions. That is, if one takes phosphonium ions we can deprotonate these phosphonium salts and we can remove one of the hydrogen atom over here, so that will give us an halide over here. So and this sort of halide we know can react with ketones to produce methylene compounds. That is the Wittig reaction you must have studied in organic chemistry. That is. So we see that for preparation of halides from phosphonium salts, one has to use organolithium reagents. The third reaction, third important reaction of this organolithium compound is carbonylation reaction. So during this reaction or during carbonation reaction, we have seen how electrophilic reagents essentially can add to double bonds, like for example organoboron compounds or Grignard reagents can react with these double bond compounds. So similarly, uh, organolithium compounds can also add to double bonded compounds, and these are very important class of reactions. One example we will see here is this reaction of ethyl lithium with isoprene here. So it will add to these double bonds, the ethyl lithium reagent, and this will essentially lead to formation of a polymer, and this polymer is known as polyisoprene, which is nothing but synthetic rubber. So this sort of carbonation reaction can also proceed intermolecularly. That is, if we take and then do lithiation. So now you remove the bromo substituent here, and this organolithium species can now again add to the double bond here, and this will lead to formation of this sort of product here after carbonation reaction. So another important variation of this carbonation reaction is where uh, organolithium compounds add to this nitrile functional group. So this sort of intermediate is formed, which upon hydrolysis will give us, which on further hydrolysis will result in a ketone. So starting from nitride, one can get ketones by doing this carbonation reaction with organolithium reagents. So similar reaction with pyridine is also known. So one can start with pyridine, that is and carbonation reaction will essentially give us this sort of intermediate, and which on heating lithium hydride will be released to give back two substituted pyridine derivatives. Again, we can also do hydrolysis, and upon hydrolysis and subsequent reaction with oxygen will give us the same product essentially will be obtained. So we can produce two substituted pyridines by carbocation reaction of pyridine of organolithium reagents with pyridines. The final type of reaction that we will discuss about of these organolithium compounds is a reaction with metal halides, and we have already discussed these reactions during our discussion on alkyl 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 ligand or preparation of complexes containing alkyl ligands, where one can use organolithium or alkyl lithium reagents and react with transition metal halides to get alkyl complexes of these transition metals. So one can do the same thing with main group halides as well. So one can do reactions like Rli plus Mx. One can remove all the M in this way. So one can do. So all the halogens can be removed to give us Rn M, this sort of product. So examples say this R4SN, or say for example R3 antimony, trialkyl antimony, or tetraalkyl, or tetra alkyl or aryl team products. Similarly, one can also remove only one of the halide groups to give us RMX and -1 here. Examples are the Grignard's reagent, so one can do reaction with MgX2 and then one can get RMgX by doing this sort of reaction. And if we add excess of RLI reagents, one can also get eight complexes like this, that is so for example tetraphenyl borate complexes can be prepared by addition of excess of these RLI reagents to these metal halides, and that will give us essentially 8 complexes. So this essentially brings us to the end of this lecture. What we have done or what we have learned during this lecture, initially we learned about how one can do estimation of organolithium reagents and why it is important to do estimation of organolithium reagents, because these reagents are used in stoichiometric quantities in different reactions, and that is why it is important to do estimation of the concentration of the reagent freshly just before performing the reactions. And this estimation can be done either by using a double titration method or by using a organic reagent, that is 4-hydroxymethyl biphenyl as the reagent. And also then we learned about the bonding in these organolithium compounds. We learned that they form aggregations depending upon different solvents. Different aggregation patterns are observed, and there is strong intermolecular forces of interaction between these aggregated units, and these essentially leads to low volatility as well as poor solubility of these organolithium reagents. Then we also learned the reason for these aggregation patterns, because we have seen that they undergo multi-center bonding, and that allows one to fill or use all the valence orbitals in lithium, or the lithium can achieve octet uh, by 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 doing by using or by using this multi-center bonding, and that is the reason why these organolithium compounds undergo aggregations. And we have also seen the MO diagram for an aggregation, that is methyl lithium, how one can form, or how four-centered two-electron bonds are formed during formation of this organolithium aggregate. Then we have also seen that the one of these sp3 hybridized orbital on this lithium atom, or the axial sp3 hybridized orbital on the lithium atom, is essentially used for intermolecular interaction or interaction with donor solvents, and that essentially brings us tells us why the aggregation pattern is different in different solvents, or how one can uh, dissociate these aggregates by using donor solvents like TMADA. Then we went on to discuss about the reactivity of these organolithium compounds. We have seen that these are very important reagents in organometallic chemistry. And with this, let me conclude this lecture. I thank you very much for being with me during this lecture.